discussion today is electromagnetic induction, a great discovery by Michael Faraday. To begin with, Michael Faraday, a British scientist who was credited with the discovery of electromagnetic induction, the principle behind electric transformer and generator, was born on September 22, 1791 in the village of Newington Butts, which is now part of London. The son of a blacksmith who faced continuous health issues, Faraday experienced a humble childhood with little in the way of formal education. His interest in science was sparked in his early teens after he started a 7-year apprenticeship in a local bookbinder and developed a love for reading, particularly the scientific texts he found in his employer's shop. When Faraday was 20, he got an opportunity to attend a public lecture series and science demonstration by well-known chemist Humphrey Davy at the Royal Institute of Great Britain, an organization devoted to scientific education and research based in the city of Westminster. Michael Faraday is credited with discovering electromagnetic induction on August 29, 1831. So, electromagnetic induction. When a DC current passes through a long straight conductor, a magnetic force and a static magnetic field is developed around it. If the wire is then wound into a coil, the magnetic field is greatly intensified, producing a static magnetic field around itself, forming the shape of a bar magnet, giving a distinct north and south pole. The magnetic flux developed around the coil being proportional to the amount of current flowing in the coil's windings, as shown here. If additional layers of wire are wound upon the same coil, the same current flowing through them, the static magnetic field strength would be increased. Therefore, the magnetic field strength of a coil is determined by the ampere turns of the coil. With more turns of wire within the coil, the greater the strength of the static magnetic field around it. But what if we reverse this idea by disconnecting the electrical current from the coil, and instead of a hollow core we place a bar magnet inside the core of the coil, the bar of magnet in the core of the coil of wire. By moving this bar magnet in and out of the coil, a current would be induced into the coil by the physical movement of the magnetic flux inside it. So likewise, if we kept the bar magnet stationary and move the coil back and forth within the magnetic field, an electric current would be induced in the coil. Then by either moving the wire or changing the magnetic field, we can induce a voltage and current within the coil, and this process is known as electromagnetic induction, and is the basic principle of operation of transformers, motors, and generators. So what Michael Faraday discovered was a way of producing an electrical current in a circuit by using only the force of a magnetic field and not batteries. This then led to a very important law linking electricity with magnetism. Faraday's law of electromagnetic induction states that a voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field, and that the magnitude of this voltage is proportional to the rate of change of the flux. In other words, electromagnetic induction is the process of using magnetic fields to produce voltage and in a closed circuit current. Increasing the amount of electromotive force or voltage that can be induced into the coil using just magnetism depends on three factors. First, increasing the number of turns of wire in the coil by increasing the amount of individual conductors cutting through the magnetic field. the amount of induced EMF or electromotive force produced will be the sum of all the individual loops of the coil. So if there are 10 turns in the coil, there will be 10 times more induced EMF than in one piece of wire, increasing the speed of the relative motion between the coil and the magnet. If the same coil of wire passes through the same magnetic field but its speed or velocity is increased, the wire will cut the lines of flux at a faster rate. Uh, so more induced EMF would be produced. The other The third factor is increasing the strength of the magnetic field. If the same coil of wire is moved at the same speed through a stronger magnetic field, there will be more electromotive force produced because there are more lines of force to cut. If we were able to move the magnets in the diagram in the simulation here, and out of the coil at the constant speed and distance without stopping, we would generate a continuously induced voltage that would alternate between one positive polarity and a negative polarity, producing an alternating or AC output voltage. And this is the basic principle of how an electrical generator works, similar to those used in dynamos in car alternators. Okay, thank you for watching.